Okay, good morning. Today, let's have a look at chapter 1, lesson 3. And today we're going to have a look at the first half of this lesson, which is about projectile motion. And next lesson, we'll have a look at the relative motion. Okay, first of all, let's have a look at the concept of projectile motion. In sports in which a player kicks, throws, or hits a ball across a field or court, the player's initial contact with the ball propels the ball upward at an angle. The ball rises to a certain point, and gravity eventually curves the path of the ball downward. If you ignore the effects of air resistance and Earth's rotation, the curved path or trajectory of the ball under the influence of Earth's gravity follows the curve of a parabola, as shown here in figure 1. The ball acts like a projectile, which is an object that is moving through the air and accelerating due to gravity. The x direction is horizontal and positive to the right, and the y direction is vertical and positive upward. So here the ball in figure 1 was hit with a tennis racket. If you draw imaginary lines through the ball images, you can trace the parabola from where the ball made contact with the racket to the other end. Another imaginary line shows the uppermost point of the trajectory, which is at the top of the highest ball. After the ball leaves the racket, its path curves upward to this highest point and then curves downward. You can see the symmetry of the ball's path because the shape of the upward bound curve exactly matches the shape of the downward bound curve. Anyone who has tossed any kind of object into the air has observed this parabolic trajectory called projection motion. Before we formally define projectile motion, we will look at its properties first. Okay, so suppose you drop a soccer ball from the roof of a one-story building while your friend stands next to you and kicks another soccer ball horizontally at the same instant. Will they both land at the same time? Some people are surprised to learn that the answer is yes. So here, as shown here in figure 2, this figure shows a struck image of two balls released simultaneously. One with horizontal projection, as your friend's soccer ball had. The horizontal lines represent equal time intervals, which is the time interval between the camera's strobe flashes is constant. The vertical components of the displacement increase by the same amount of each ball. The horizontal displacement of the projectile, in this instance, the ball, is called the horizontal range, which is usually denoted by delta dx. The horizontal motion is also constant. The trajectory forms from the combination of the independent, horizontal, and vertical motion. We observe the following properties about the motion of a projectile. First, the horizontal motion of a projectile is constant. Then, the horizontal component of acceleration of a projectile is 0. Next, the vertical acceleration of a projectile is constant because of gravity. And last, the horizontal and vertical motions of a projectile are independent, but they share the same time. So combining these properties can help us define projectile motion. So by definition, projectile motion is the motion of an object such that the horizontal component of the velocity is constant and the vertical motion has a constant acceleration due to gravity. The most important property of projectile motion in 2 dimensions is that the horizontal and vertical motions are completely independent of each other. This means that motion in one direction has no effect on motion in the other direction. This allows us to separate a complex 2-dimensional projectile motion problem into 2 separate simple problems. One that involves horizontal uniform motion and one that involves vertical uniform acceleration down. So here, as shown in figure 3, this figure shows a basketball player hitting a fly ball and the path it follows. You can see that the horizontal velocity Vx is independent of the vertical velocity Vy. You can also see this result in the stroke images in figure 2. The ball on the left simply drops, but the ball on the right has an initial horizontal velocity. The ball on the left falls straight down, while the ball on the right follows a parabolic path typical of a projectile motion. The balls have quite different horizontal velocities at each flash point in the image. Nonetheless, they are at identical heights at each point. This shows that their displacements and velocities along the y direction are the same. The image confirms that the motion along the vertical direction does not depend on the motion along the horizontal direction. Okay, so now let's have a look at how we can analyze the projectile motion. So in previous sections, we have reviewed the equations that describe motion in 1 dimension, right? You can use these same equations to analyze the motion of a projectile in 2 dimensions. You can simply apply the equation to the x and y motions separately, because for each direction, that's simply a motion in 1 dimension, right? Assume that t equals 0, the projectile leaves the origin and an initial velocity vi. If the velocity vector makes an angle theta with the horizontal, where theta is a projection angle, then from the definitions of the cosine and sine functions, we have the following relationship. Okay, first of all, the horizontal component, Vix, which is a horizontal component of the initial velocity, is Vi times cosine theta. And Viy, which is the initial velocities component in the vertical direction, equals Vi times sine theta, where Vix is the initial velocity, which is at t equals 0 in the x direction, and Viy is the initial velocity in the y direction. Also note that these numbers should have either positive or negative symbols in front of them. Negative symbols means the direction is to the opposite of your specified positive direction, okay? So here, table 1 summarizes the kinetics equations we can use with both horizontal and vertical components. So in horizontal motion x, we can have a constant velocity equation for the x component, which means Vix equals Vi cosine theta, and Vix is constant. Also, because it's a constant velocity motion, then we have the displacement in the x direction equals Vix times delta t. And put all the values in, you can have delta dx equals Vi times cosine theta times delta t. And along the vertical motion, which is in the y direction, you know that's a constant acceleration motion, right? The constant acceleration has a magnitude of about 9.8 meters per square second near the surface of Earth. Then we have the following relationship. Vfy equals Vi sine theta minus G delta T. Delta dy equals Vi sine theta times delta T minus 1/2 G times squared delta T. And squared Vfy equals Vi sine theta squared minus G times delta dy. Also, you should be careful with the positive or negative symbol in front of each quantity here, okay? If the direction of a quantity is in accordance with the positive direction you specified, the number should be positive, otherwise that should be a negative number. Okay, so now let's have a look at a sample question to illustrate these concepts. Well, let's consider this question here. Airplane carries relief supplies to a motorist stranded in a snowstorm. The pilot cannot safely land, so he has to drop the package of supplies as he flies horizontally at a height of 350 meters over the highway. The speed of the airplane is a constant, which is at 52 meters per second. Figure 4 shows the packages as it leaves the airplane, or in mid-drop, or when it lands on the highway. So there are two questions. First, calculate how long it takes for the package to reach the highway. Then determine the range of the package. Okay, I'll give you 5 minutes to consider this problem by yourself, and then we'll have a look at the solution together. Okay, have we finished? Then let's have a look at the solution together. So in question A, we are given delta dy, which is -350 meters, and initial velocity is 52 meters per second. And we want to calculate delta t, right? So we can set di, which is the initial velocity equals 0, as the altitude at which the plane is flying. Therefore, delta dy is -350 meters. So we can calculate delta t from the formula for displacement along the y direction. Delta dy equals vi times sine theta delta t minus 1/2 times g times squared delta t. Okay, so following this concept, we can find delta dy equals -1/2 times g times squared delta t. And from this equation, we can find delta t is square root of -2 times delta dy over g. And then put all the values in, we have delta t equals 8.45 seconds. So the package takes about 8.5 seconds to reach the highway. Any questions? Okay, so for the second question, we are given, again, delta dy equals -350 meters. Vi equals 52 meters per second, and we have already calculated that delta t equals 8.45 seconds, right? So this time we require delta dx, which is the range of the package. So we can calculate delta dx using the definition of cosine. Delta dx equals vi times cosine theta times delta t. Then delta dx equals 52 times cosine 0 degrees times 8.45, and this gives us 440 meters. So the range of the package, well, if we use scientific notation, that should be 4.4 times 10 raised to the power of 2 meters. Okay, so have a look at the solution here. Do you have any questions? All right, if you don't have any questions, let's consider another practice question. Okay, so this time we have a golfer who hits a golf ball with an initial velocity of 25 meters per second at an angle of 30 degrees. So this time we have an angle of 30 degrees here above the horizontal, which is illustrated in figure 5 here. This golfer is at initial height of 14 meters above the point where the ball lands. Then, can you calculate the maximum height of the ball? And then determine the ball's velocity on landing. Okay, again, I'll give you 5 minutes to consider this question by yourself, and then we'll have a look at the solution together. Okay, so let's have a look at solution of this problem. So first of all, you have to choose a reference point, right? So suppose we choose the golfer's initial position as a reference point, then the maximum height of the ball is the highest height of the ball with respect to the golfer at its initial position. So we are given the initial velocity of the ball is vi equals 25 meters per second, and the angle that the initial velocity makes with the positive horizontal direction is 30 degrees, and we require the delta dy max. So when the golf ball reaches its maximum height, the y component of the ball's velocity is 0, right? So actually, there are a number of ways we can solve this. You could either solve the time taken for the ball to reach the highest point first, and then find the highest highest delta d. Or you can also use vf squared minus vi squared equals 2gs, 2g delta t, right? Okay, suppose in this question, we are going to find the time taken to reach the highest point first. Okay, so we have the following relationship. Delta dy equals vi times sine theta times delta t minus 1/2 times g times delta t squared, right? So on the other hand, we have vfy equals vi sine theta minus g delta t. And put all the values in, we have delta t equals vi sine theta over g. This gives us 1.28 seconds. And then we can find delta dy max equals vi sine theta delta t minus 1/2 g times delta t squared. Then you have all the numbers ready there. So plug these values in. We have delta dy max equals 8 meters. So the maximum height of the ball is 8 meters with respect to the initial position of the golfer. Okay, then let's consider question B. In question B, we're given, again, initial velocity, and also we have calculated, we have known that delta dy is 14 meters. So we can, if we set di, which is the initial velocity, initial displacement at the point at which the golfer struck the golf ball, then we have delta dy equals minus 40 meters, right? So it all depends on which reference point you choose. Then use the equation vfy squared equals viy squared minus 2g delta y to calculate the final vertical velocity of the ball before it hits the ground. Then calculate the velocity when the ball lands using vf equals the square root of squared vfx squared plus vfy squared and the inverse tangent ratio. Okay, so following this logic, we have vfy squared equals viy squared minus 2g delta dy, which equals vi sine theta squared minus 2g delta dy. So put all the values in, then we have vfy is either positive or negative 20.8 meters per second. We have to choose a negative number because the object is moving down, which is opposite to the positive direction along the y-axis you choose, right? Then Vx equals Vi times cosine theta, which is 25 times cosine 30 degrees, which is 21.7 meters per second. Then we know final velocity Vf is a square root of Vx squared plus Vy squared, and this gives us 30.1 meters per second. So this is the magnitude of the final velocity. And the angle that this velocity makes with the positive horizontal direction is arctangent 20.8 over 21.7, which is about 44 degrees. So the final statement is the velocity of the ball when it lands is 30.1 meters per second with direction 44 degrees below the horizontal. Okay, have a look at this question. Do you have any questions to ask? Okay, if no questions, let's have a look at another concept, which is the range equation for the projectile motion. So when you know the initial velocity and launch angle of a projectile, we can then calculate the projectile's range, which is usually denoted by delta dx. Now suppose we launch a projectile that lands at the same height it started from, as shown here in this figure 6. In this case, delta dy equals 0, right? Because the total displacement is 0. And we can use total displacement in the y direction is 0, right? Because it lands at the same height it started from. And we can use this fact to significantly simplify the equations of motion. We can calculate the range using the equation delta dx equals vix times delta t, if we know the initial velocity and the launch angle. So to determine the value of delta t, we can use the equation for vertical motion. VIY, which is initial velocity's component along the y direction, equals VI times sine theta. Delta dy equals VI sine theta times delta t minus 1/2 times g times delta t squared. The final level is the same as the initial level, so delta dy equals 0, right? Substituting values in the vertical motion equation gives us 0 equals VI sine theta times delta t minus 1/2 times g times delta t squared. Well, put the common factor delta t in front, we have 0 equals delta t times VI sine theta minus 1/2 g delta t. Therefore, we have either delta t equals 0 on takeoff, or VI times sine theta minus 1/2 g delta t equals 0 on landing. Solving this later equation for delta t gives us the following equation. Delta t equals 2VI sine theta divided by g. Now we return to the equation for range. The range delta dx equals initial velocity vi in the as a component of the initial velocity along the x-axis times delta t, right? Substituting delta t and the initial velocity in the x direction, we have vix equals vi cosine theta. This gives the delta dx equals vix times delta t, which is vi times cosine theta times 2vi sine theta over g. And simplify this gives us delta dx equals vi squared over g times 2 sine theta cosine theta. Also note that in mathematics, we know 2 sine theta cosine theta is sine 2 theta, right? This is according to the double angle formula. So the final solution is here. This is a range of such a projectile motion. The range of this projectile is delta at dx is given by vi squared over g times sine 2 theta, where vi is the magnitude of the initial velocity of a projectile launched at an angle theta to the horizontal. Note that this equation applies only when delta dy equals 0. That is, only one projectile lands at the same height from which it was launched. The largest value of the range is when sine 2 theta equals 1, because the sine function has a maximum value of 1, right? So this maximum value occurs when the angle is 90 degrees. Since 2 theta equals 90 degrees, then theta must be 45 degrees. So we know the largest value of the range can occur when theta equals 45 degrees, right? So all the previous discussion and examples of projectile motion have assumed the air resistance is negligible. This is close to the true situation in cases involving relatively dense objects moving at low speeds, such as shot used in shot put combination. However, for many situations, you cannot ignore the air resistance. When you consider air resistance, the analysis of projectile motion becomes more complex and is beyond the scope of this context here. So let's have a look at a sample problem in which we use kinematics equations to calculate the maximum height and the range for a projectile. So now let's consider this question here. Suppose you kick a soccer ball at 28 meters per second toward the goal at a launch angle of 21 degrees. Two questions you need to answer. First, how long does the soccer ball stay in air? Then determine the distance the soccer ball would need to cover to score a goal, which means you need to find the range of the soccer ball. Okay, again, I'll give you 5 minutes to think about this question by yourself first. All right, let's have a look at solution to this question. Okay. Question A, we are given initial velocity is 28 meters per second and direction theta is 21 degrees, which is the velocity makes with the positive horizontal direction. And we need to find delta t. Okay, so according to the range function, range formula, we have delta t equals 2vi sine theta over g, right? Then we know vi, we know theta, then put all the values in. Delta t equals 2.0 seconds. So the soccer ball will stay in the air for 2.0 seconds. Oh, sorry, not the range formula. That's the formula for delta t. In second question, we need to use the formula for the range, right? The range of the soccer ball is delta dx is vi squared over g times sine 2 theta. And we know vi, we know g, and also we know theta. So put all the values in. The solution is delta dx is 54 meters. So the range of the soccer ball is 54 meters. Okay, any questions? Okay, if you don't have any questions, that's the end of today's class. Remember to complete your homework in Google Classroom and submit them before the deadline. Okay, I'll see you next time.